So let's talk about fibred categories. Since we are ultimately working up towards the concept of a stack, and we can sort of think of a stack as a sheaf of categories, we had better first introduce the concept of a pre-sheaf of categories, quote unquote, and that is a fibred category. So a fibred category on a category C is a functor that goes from the opposite category of C to the category of small categories, or of locally small categories, or something like that. That's it, that's the definition. Now the problem is that the category of categories isn't really like your run-of-the-mill category. Especially you can't really talk about equality of functors. So we actually need to specify a bit what we mean. So first thing, what is a functor? Functor acts on objects and on morphisms. So for every object X we have a category. Let's call our functor f. Category f of x. And for every morphism going between x and y, we have a functor. And now note, because of the the functor has to go in the other direction, f of f going from f of y to f of x. Now usually you would have the condition of everything working nicely with respect to composition, but we can't really talk about equality of functors. The best thing we can talk about is natural isomorphism. So we actually need to provide a natural isomorphism such that for f going between x and y, so morphism in C, and g going between y and z, we have a natural transformation, or natural isomorphism really, CFG going between. Now if we have the morphisms like that, then we can compose G after F. Then by applying the functor F it should be turned around, so we have f of f after f of g going to f of g after f. And this natural isomorphism has to work well with associativity, so there's also a commutative diagram. If we introduce a third morphism into the mix, such that for f from x to y, g from y to z, h from z to w, we have, well, first we can compose all of them together. We have h after g after f. Then we can split off one of them, so f of f after f of h after g. Or we can split off the other one, f of g after f, f of h, and then in both cases we can split off the rest, so we have f of f, f of g, and f of h. And now this here is c of f and h after g, this one is c of g after f and h, and then here we have identity vertically composed with cgh, and here we have cfg vertically composed with the identity, and this should commute. And of course we also have another natural isomorphism, I guess u from the identity functor on fx to f of the identity of x. So for every object x, a natural isomorphism u of x that has to play nicely with our composition. So if we have a morphism f between x and y, then we have a functor f of f from f of y to f of x, and we have f of the identity on y after f, and that is the same thing because identity composed with any function is just that function. Same goes for f applied to f after the identity on x. Now we can map using c of I dy and f. We have f of f after f of I dy. Similarly here we have c of f and I dx. No, it has to be the other way around. F I dy, and here we have I dx f. That goes to f of I dx after f of f. And then we can map from f of f composed with the identity functor using the identity natural transformation composed with u of y, and this is just the same as the identity functor composed with f of f, and we can map using u of x composed with the identity natural transformation. And then of course that is also equal, and this diagram has to commute as well.